Welcome everybody to this seminar. It's always a pleasure to host an ex-student of ours. And Abdullah graduated from LUMS, I think, in the year 2021. And since then, I think he's been at Urbana-Champaign. He's should now be close to finishing his PhD, I assume. He works on fault-tolerant quantum computing, and we're very excited to have him over. Abdullah, all over to you, please.
Sir.
This is easy.
So I wanted to present my work briefly, the experiments I've done over the past 4 or 5 years. And I also wanted to give an introductory talk on superconducting circuits. So I sort of combined both of these into a single talk. We don't have to go through all the way, but I hope there's something in here for the very beginners who have no idea what these circuits are, and also for the experts who know the physics and just want a review of what's going on in the field right now. So this is going to be the outline of my talk. First, we're going to spend a good amount of time on briefly going through what superconducting quantum devices are, what these circuits look like, how we measure them, why they actually behave like quantum circuits. Next, we're going to go into the meat of the talk, which is my area of research in the lab. We're interested in networks of these quantum devices or networks of these quantum circuits, and we'll try to answer the very simple question of whether or not we can perform high-fidelity gates between qubits that are on separate chips in different modules. And then finally, based on this architecture I'm going to describe, we're going to talk about a very physically interesting experiment that we recently did last year, which is related to entanglement stabilization. What that means is you have 2 qubits that are entangled for as long as you want. The entanglement doesn't decay away. So those are the 3 main topics we're going to discuss today. So let's start off with the basics. Now, if you open any review paper, this is how the introduction to quantum circuits usually starts. We're all familiar with the LC oscillator. You have an inductor, you have a capacitor, and you can write down the total energy of the system as the sum of the capacitive and the inductive energies. And this sum, the total energy, let's call this the Hamiltonian for now. Omega, of course, 1 over square root LC is the frequency of this oscillator. Now, let's assume we can operate in a quantum regime, where I'll talk later about why that's possible. But under that assumption, we can use the typical recipe for quantization. So anyone who's taken a second course on quantum mechanics goes through this recipe. We promote our operators, the charge and the flux, we promote the flux, charge and flux variables to operators, to non-commuting operators. And then we express those as in terms of ladder operators. And that allows us to write this Hamiltonian as a quantum harmonic oscillator. And the energy level diagram, of course, looks like this. The energy levels are equally spaced. And if you provide a photon with energy h bar omega r is the frequency of the resonator, then you populate the first Hawk state of this oscillator, and you can keep on adding more photons. That's your typical quantum harmonic oscillator. And we can get to that if we can operate this circuit in the quantum regime. Now, the interesting question, and something we often skip over, is why can we even operate this in a quantum regime? What conditions do we need to actually make this work? And we can basically boil it down to these 2 conditions. First is your oscillator, your LC oscillator, should be significantly decoupled from the environment. And that's important because if you populate your circuit with 1 photon, with 1 excitation, that excitation should stay there for long enough for you to treat it as a quantum state. If it's too strongly coupled to the environment, you populate it with a photon, and the photon immediately decays, and you can't really operate it as a quantum system. The second requirement, of course, is that the energy separation between the levels of the harmonic oscillator, they should be much larger than the thermal energy of the environment. So if your environment is too hot, then you're just populating your resonator with thermal photons, and you can't really have a quantum state anymore. So that's why we cool down these circuits to very low temperatures, and we make these circuits out of superconductors. That allows us to have photons in there for long enough times, and those photons, you can actually have Fock states in your resonator because it's significantly at a very low temperature. So when we see these images of superconducting processors from Google, IBM, or any of these companies, this processor contains these circuits that we're talking about, and for them to actually behave like quantum circuits, they need to go into what we call a dilution fridge. So if you ever search up an image of a quantum computer, this usually shows up, but that's just a dilution fridge that brings it to a low enough temperature for it to operate. So the circuit goes at the very bottom stage of this dilution fridge, which typically is at around 10 millikelvin. At this temperature, the thermal photons are there's very few thermal photons, so you can actually send in single photons into your resonator and have Fock states.
Why is it called the dilution fridge?
There's a process that goes on which requires both helium-3 and helium-4. And I'm not sure about the technical details, but there's some part of the process is related to dilution, and that's why they call it that. So as you move down to these stages, you get lower and lower temperatures, starting from 100 millikelvin to 50 millikelvin, down to 10 millikelvin. So that's how we can treat these as quantum circuits. Those are the conditions. Now let's dive slightly more into the physics. So you have this circuit. It's at a low enough temperature. It's made out of a superconductor, so you can treat it as a quantum harmonic oscillator. Now, how do we populate it with photons? We apply a microwave drive. It's microwave because the dimensions of these circuits are on the orders of centimeters. So if you calculate the resonant frequencies, they turn out to be in the microwave regime. So you need to send in a microwave drive to populate it with photons. If my drive frequency is omega r, I'm going to populate my resonator. But there are a few problems. Because these levels are equally spaced, I can't really control them individually. If I turn on this drive, I'll just climb higher and higher in the ladder, and I'll just keep populating my resonator with photons. So that's a problem, because if we're interested in quantum information, we want unique control over each of these energy levels. I want to be able to prepare ket 0, ket 1, or ket 2, or ket 0 plus ket 1. So that means the harmonic oscillator itself isn't really useful if you want a qubit. There are ways to treat it as a qubit, things like bosonic codes, but we're not going to dive into that. For now, we're going to see how we can modify this circuit so we can individually address these levels. So that's where the most common kind of superconducting qubit comes in. You might have heard of the transmon qubit. And the transmon qubit is almost a quantum harmonic oscillator, but there's a slight anharmonicity. So when you have an anharmonic oscillator, your energy levels are going to be differently spaced, so you have individual control over the levels. So the requirement is some nonlinearity in the circuit, and that comes from this famous element called the Josephson junction. It's a nonlinear lossless superconducting element. And the way we fabricate this is to simply have an insulator sandwiched between two layers of superconductors. That gives you the Josephson junction, and you have Cooper pairs tunneling across this junction. That gives rise to this nonlinear term in the Hamiltonian, which is minus ej cosine of phi, where phi is the phase difference between the superconducting condensate living both sides of this junction. Now, the important part here is that if you replace your ordinary inductor with the linear inductor with this Josephson junction, your Hamiltonian changes into something like this. Now, if you follow the same quantization recipe and we expand this cosine up to the fourth order, this is the Hamiltonian you get. Now that's really interesting because the first term is simply a harmonic oscillator, and the second term is some nonlinearity, which means that your levels are not equally spaced anymore. And this is what the potential now looks like. Now this is really useful. The separation between the first two states is omega q. We're calling this the qubit frequency. And the next one is different by an amount called EC. So that means if I now send in a microwave drive at this particular frequency, I won't be able to populate the third level. And what happens is I can drive Rabi oscillations between the G and the E levels. So that means we have a qubit, an approximate qubit. Of course, there are problems that arise because it's not exactly a qubit. We're not going to dive into those. But if you treat it well enough and you work in a low power regime, it's a pretty nice qubit. So that gives us two ingredients to work with. We have simple harmonic oscillators, and we have something we can approximately treat as a qubit. Now the next step is what happens if we couple both of these? If we capacitively couple both of these circuit elements? We're going to see why that's important in a bit. But for now, let's just look at the Hamiltonian for this simple circuit over here. You have your harmonic oscillator, then you have your qubit. We're going to treat the transmon as a qubit from now on. And then you have this exchange term, and this Hamiltonian is simply the Jaynes-Cummings Hamiltonian. Now that's important because that means you can have light-matter interaction on a chip. Instead of requiring an actual cavity and an atom trapped inside, you can do all of this on a chip. But for now, we're not really interested in the Jaynes-Cummings Hamiltonian. You can simulate light-matter interactions if you're interested in them. But right now, we're looking in a different regime. And this is called the dispersive regime, which we can achieve if the qubit and the resonator frequencies are very different. If the difference between them is much larger than their coupling strength, you can make certain approximations. And what you get is the dispersive Hamiltonian. This is really useful because what this tells you is that the qubit state depends on the resonator, or you could say the resonator state depends on the qubit. And it's easy to see if we write the Hamiltonian in a slightly different way. If we recombine these terms, you can see that the coefficient of A dagger A, which is the harmonic oscillator, is now its bare frequency, omega r, plus some constant times sigma z, which comes from the qubit term. What that means is that this coefficient, and remember the coefficient is actually the frequency of the oscillator, it now depends on the state of the qubit. That gives us a way to read out the state of the qubit. So if my qubit is in 0, the resonator frequency is omega r. If my qubit is in the first excited state, it's omega r plus chi. That means if I can simply probe my resonator, I can read out what my qubit state is. So that's what we call dispersive readout.
How about the last term?
The last term, that's simply the bare frequency of the qubit itself.
So if sigma z is 1, that will add up to that, huh?
Yep, that's correct. But when we're actually going to probe the resonator, we're simply effectively measuring the coefficient of this term over here.
Okay.
So for a simple experiment, we can, this is what the circuit would look like. We have one port where we can send in a drive to prepare the qubit in the ground or the excited state, and a second port that allows us to read out the frequency of the harmonic oscillator or the resonator. And this is what the actual data looks like. I'm not going to go over the actual details of how we convert this signal into these values over here. But in very simple words, we send in a signal over here, it gets reflected back, and the reflected signal contains information about the frequency and the phase of the resonator. And that can be plotted in this certain way. So each dot over here is one shot or one measurement of the resonator. And you can see that if you do thousands of these measurements, you get these statistics, and there's a clear dependence on the state of the qubit itself. So we call these readout blobs, and each blob corresponds to a certain state of the qubit. So once I have these statistics, I can draw a line exactly in between these two, and that tells me how to discriminate between the states of the qubit. So if my next measurement shot falls towards this side of that line, I know my qubit is in the ground state. If it falls on the other side, I know it's in the excited state. So now we have our qubit. We know how to read out the qubit, and that's
There
basically.
is obviously some gray area over here, right?
Yes, of course. And that means that you only know your qubit state with a certain amount of confidence, let's say 99%. That's what we call the readout fidelity. Even in the best processors these days, the readout fidelity is around 99.99 or 99.9%. And that's a big problem with superconducting circuits. It's because readout is difficult and there's always some error associated with it. So once you run your circuit or your algorithm, you have to correct for this gray area. Okay. So that's just a brief introduction to superconducting circuits. Of course, I'm not going to go over what happens if you couple different qubits together. Of course, that's important. That's how you get 2-qubit gates. That's how you get entanglement. But we're going to come to that later. So this is what these circuits usually look like. And whenever you see a picture of a processor like this, it's basically just a bunch of these trans-1 qubits along with the readout resonators. So typically each qubit gets its own harmonic oscillator that allows you to read out the state of the qubit.
What does the readout oscillator physically look like?
So physically, it can be of different forms. We can quickly jump to my backup slides where I have an image. So there are many different ways of fabricating these on chip. So here's one of the devices I fabricated last year. So this is my chip, this sapphire wafer, and this long strip line is the readout resonator. So it's basically just a piece of metal that has a normal mode, and that normal mode is what I'm calling the quantum harmonic oscillator. And this small thing right next to it is the trans-1. So the proximity of these two elements basically gives the coupling between them.
But zoomed in, like, let's say, I mean, like, not at this level, but what kind of material? It's just a piece of metal, is that it?
It's just a piece of superconductor.
It's just a strip of wire.
That's it. Yeah, a very thin strip of
A
wire.
very thin strip of wire.
Yes.
Okay. Want to talk to you about that afterwards.
Oh, definitely.
Good.
So this is essentially a transmission line that can be, modeled as a inductor and a capacitor.
Yeah.
So that's just a basic introduction. Next up, we're going to talk about what we're actually doing in the lab and significance of what we're trying to achieve. So we see these processors from different companies, from Google, IBM, and other companies. And these processors, the very best of them contain a few hundred qubits at the very best. And that's been a significant problem in the field because people are finding it hard to add more qubits to the same chip. And there's a bunch of different reasons. First, of course, these aren't really very small circuits. If you look at the size, each element can be up to a few centimeters, or let's say 1 centimeter chip. Of course, that's one problem. The other is the yield. So these circuits, you need to go into the clean room and fabricate them. The fabrication process is quite dirty in some sense. So all of your qubits don't end up always working. You try to make 100 qubits, 10 of them are going to be bad, and that just ruins your chip. So even these companies like Google and IBM have to fabricate the same chip hundreds of times to get one that actually works. And then, of course, there's the problem of crosstalk. These qubits also interact with each other. So the closer they are on the chip, the more crosstalk there's going to be. And that just adds more errors to your single qubit gates, to your 2-qubit gates. So in every sense, it doesn't seem like a nice idea to keep on trying to add more qubits to the same chip. So a lot of people are thinking of modular quantum computing. Many people believe that we won't have more than a few thousand qubits on the same chip. And in order to scale up to go to hundreds or thousands of qubits, you need to combine different chips together in some way so that the errors don't transfer from one chip to the other, but you can still have a larger number of qubits working together. And of course, the reason we want to go this way is because we want to increase the number of qubits while reducing the error. This is a graph that my advisor has often used in the slides, and it's a nice illustration of where we are with our current hardware and where we want to go. You can see that we can go probably up to thousands of qubits, but the error rates are quite high. So you have 1 in 1,000 chance of having an error on average, and that's pretty low for the applications of quantum computing that we actually want to achieve. So if you want to get up to these numbers for factorization, for quantum chemistry, stuff like that, there's a lot that we have to fix. And we think modular quantum computing might be one way to scale up the number of qubits and reduce the error rates. So here's a few recent figures. This is from a group in China that actually tried to connect two of their chips together using a cable. This is just to show you what these devices may actually look like. And this is one from IBM, where they have two of their processors, and they're connecting them by something they're calling L couplers. That's all the information we have. They don't really share much more. But that's just to say that these companies are also looking towards modular quantum computing as the next step. Now let's go on to what we're doing in the lab. This was our first experiment when I joined the lab. It's a very simple one. We have two of these modules. Each of them contains 1 qubit. And we couple them together with this coaxial cable. Now this is just to show what it looks like, but what's relevant is just the circuit diagram over here. The cable in the center, of course, supports some normal modes. We can use one of those normal modes as a resonator or as a harmonic oscillator. And then each of these modules contains a qubit that's capacitively coupled to the normal mode. So that's what the circuit looks like. So you see 2 ports over here. One of them is for reading out the resonator, the readout resonator, and the other one is for controlling the qubit. And this is just a diagram of what this cable looks like inside the module. You just have this piece of metal poking into the module, and that allows you to couple your cable to the transmon qubit. Now let's dive into the physics of how this experiment actually works. The simplest thing you can do between two of these modules is simply to swap a quantum state from one module to the other one. That's the simplest 2-qubit gate you can come up with. And the way this works is you first need to figure out, of course, a way to transfer your quantum state from the transmon to what we're calling the bus or the resonator, and then from the bus to the second transmon. That completes your 2-qubit gate, which is simply a swap gate. And the way we achieve this is by taking advantage of the multi-level nature of the transmon. So remember I said that the transmon is only approximately a qubit. It has a higher level structure given by the cosine potential. And that means you can use it as a 4-wave mixer. That's something that people from quantum optics may be familiar with. If you have a chi-3 material, it acts as a wave mixer. You send in 2 waves of different frequencies, and you can get a 3rd wave at the output, which is a sum of their frequencies or a difference of their frequencies. Now, the reason that's important is that I can send in certain frequencies to this transmon, and if they match, if the frequencies that I send in add up to the difference between the transmon and the resonator frequency, I can convert a photon from the transmon to a photon in the resonator. And this energy level diagram over here shows what's going on. The red one is the first transmon, the green is the resonator, and the blue is the second transmon. So if I want to transfer an excitation from this transmon to the resonator, I simply need to send in 2 photons that add up to the frequency difference. And so once I do that, my photon is transferred into the resonator or the bus. This is something we call 4-wave mixing, and it's simply allowed because the transmon has a multi-level structure. Now, of course, the next step is once your excitation is in the resonator, you need to transfer it into the second transmon, and that's simply an identical process. this energy level diagram over here. I repeat the same part on the second transmon, and that transfers the excitation from the resonator to over here. Now, if we turn on these drives that provide these purple photons, we can plot the population of both of these transmons as a function of the duration of these drives. And you can see that the population oscillates between both of them. We start off with the photon in the first transmon. After around 100 nanoseconds, it's completely gone from the first one. And the second one has a population that reaches 1, which means that the photon is transferred to the second transmon. So that's what we call sideband transitions. And if you simply turn off the pump over here, you've successfully done your first 2-qubit gate, which is a swap gate between the 2 qubits. And this swap occurs in less than 100 nanoseconds, which is comparable to very fast, the fastest gates that we have in superconducting circuits. And the loss that we have per swap is around 1%. And that's a big jump over the previous demonstrations of similar experiments. So a few years ago, a group at Yale came up with this idea. They did this experiment and they had loss rates of around 20 to 25%. So our goal was to bring that error down to sub-percent. And the reason that's important is because once you get to this level of error, your architecture becomes compatible with quantum error correction because the thresholds for a lot of different error correction codes are around 1%. So this means you can have a quantum network, you can have 2 chips connected together, and you may also be able to do error correction on both of them.
And what you did differently compared to the experiment that had?
So there were a few major differences. The first was, of course, the hardware. This connection scheme we came up with is custom built. People in previous experiments, people were just using commercial parts, which were really lossy. We had to design all these parts and machine them ourselves, just so the error rate was low, just so you're less likely to lose your photon while it's traveling from the first qubit to the second qubit. And the second difference is, of course, this sideband transition that we're using to transfer the population from the qubit to the bus. This is called degenerate 4-wave mixing because both of these photons have the same frequency. The standard in the field used to be non-degenerate 4-wave mixing and the reasons are mainly technical. People used to stick with non-degenerate. We just did some math and we realized that if these 2 photons have the same frequency, you can drive your transition twice as fast as the usual one. So you could say it's a combination of the scheme that we used and slightly better hardware that allowed us to get to 1% errors.
So did you test it only for the ground and excited state or also for superposition states?
We did it for superposition states as well. We tried to entangle both the qubits by using a superposition state. I don't have the data for that over here, but we've tested that for the paper.
And what was the accuracy for that?
So for the superposition state, I don't have a number for the error we had in the swap, but the entanglement fidelity using this scheme was around 97%. And that was only limited by the T1 and the T2, the dephasing times and the relaxation times of the qubits themselves.
And how did you measure this? I'm assuming any measurement of this kind of a thing is kind of like a destructive process.
So when we're reading out, using the readout resonator. You measure the resonator, the state of the qubit, and ideally that's a QND measurement. So it shouldn't destroy the state of the qubit. Will of course collapse it. It's a projective measurement, but it shouldn't destroy the state of the qubit. But in any case, each of these measurements is separated by a long time duration. So once you measure the qubit, you project it into 0 or 1. Then just to be safe, we wait for a long amount of time before we do the next run of the measurement so that every time we know that the qubit is actually starting in the ground state. That's something we ensure simply by waiting for a long time before each run of the measurement. Okay. So just to summarize, this is the simplest 2-qubit gate you can do between two of these chips. And it served as a test for our modular architecture. We just wanted to make sure that the loss rates are low enough that we can actually scale this up and do more complicated experiments using this architecture. The next experiment I wanted to discuss is, it's less practical, but it's more physically interesting. The thought process was simply that we have an interesting architecture. Is there any interesting physics we can do with this? And that's where we became interested in entanglement stabilization. So before we dive into that, there's something I wanted to introduce, which is what we call remote entanglement. So we have this architecture, we have these modules, and these qubits, we can call them remote qubits because they're far away. They're spatially separated from each other. So how does entanglement typically work in this case? You have two qubits that are far away, let's say on different chips. How can you entangle them? There are two main ways to do this. The first one is something we call pitch and catch, and that's pretty straightforward. You send out a photon as a wave packet. It goes into a transmission line and it's absorbed by the second qubit. And this way you can have entanglement between two of your qubits. The second way is based on Bell state measurements. You prepare your two qubits in superposition states. You send out the wave packets. Then you perform Bell state measurements on the photons. And that projective measurement simply collapses your two qubits into one of the Bell states. These are the two typical ways remote entanglement is done. But we wanted to take another step in a slightly different direction. We were wondering if you can do this in the steady state instead. And what I mean by that is both of these protocols prepare an entangled state, but the entangled state decays after a certain amount of time because your qubits have finite relaxation times. They have a finite T1 and a T5. T5 is the dephasing time, T1 is the relaxation time. So in our field, the typical relaxation times are a few hundred microseconds. So that means your entanglement only stays for that amount of time. After a few hundred microseconds, your state decays. You have to start over. You have to prepare your entanglement again. But can you have entanglement in the steady state such that it stays entangled for as long as you wish? That's something we were interested in. And that usually leads to bath engineering and open quantum systems. Because if you have a quantum system that's well protected from the environment, you can try it as best as you can, but it's still going to decay after a certain amount of time. So if you want to keep any quantum state alive for arbitrarily long, you need to use the environment to your benefit. And that's what we call bath engineering. So let's say you have these two qubits, and they're strongly coupled to a bath, which simply means you can observe your quantum state. Something is observing your quantum state, so we can call it the bath or the environment. And if you want steady state entanglement, you need to generate a certain kind of loss operator, which we call a joint loss operator. So when I mention the loss operator, I'm talking about the Lindblad master equation. The master equation takes in a certain loss operator, which tells you how your qubit or your quantum system interacts with the environment. And if you can somehow engineer a collective loss operator, you can have steady state entanglement under certain conditions.
So entanglement was already generated, right?
Yep.
But if it is interacting with the environment through this loss operator, won't the entanglement be destroyed itself?
So in this case, we want this loss operator to generate the entanglement.
Okay.
Yep. So this loss operator is going to be what takes your qubit from the ground state into the entangled state. Then, of course, you are going to have other forms of loss, which are not collective loss operators, which are simply the individual loss operators of the qubit. And those are, of course, going to be harmful. They're going to destroy the entanglement that you're trying to make using the joint loss operator. So this is just a brief overview of the physics that we're interested in. Many people have done this in different sorts of experiments. For example, this one, you have two qubits that are placed inside a cavity. The cavity is lossy, it's interacting with the environment, and if you apply the appropriate drives, you can have steady state entanglement in the system. Then of course,
These drives are the path, right?
so the drives, we treat the drives as part of the closed quantum system, and we treat only the loss as the environment. So you could say the drives are simply going to be the sigma x terms in your Hamiltonian, and you need those to generate the right kind of Hamiltonian, which under this loss gets you entanglement. So there are a few different experiments. I won't go into the details. I just provided the papers in case anyone's interested in these. But the idea is you generate this loss operator somewhere, and that gets you steady state entanglement. But all of these results were on the same chip. So it wasn't actually remote entanglement stabilization. There was entanglement stabilization between two qubits that are sitting right next to each other on the chip. We were interested in a remote setting. And that leads us to this very interesting protocol that was proposed more than 10 years ago. So the system we're interested in is two qubits coupled to a chiral waveguide. A chiral waveguide simply means photons can only propagate in one direction in this waveguide. So what happens is this qubit loses photons to the waveguide. They travel downstream. They can get absorbed by the second qubit, or they can just flow further downstream. Now what happens is we drive both of these qubits. Of course, we want steady state entanglement. So if you're constantly losing your photons to the waveguide, you need something to pump those photons back into the qubit. Otherwise, you'll just decay into the ground state. So this system is called a coherent quantum absorber. What that means is, under the right conditions, you drive both of these qubits simultaneously. All the excitations or the photons leaving the first qubit are absorbed perfectly by the second one. And if that happens, you have no emission over here. And that, under those conditions, you can have a very interesting steady state that's actually entangled. So I'll first go over the requirements for the protocol, and then I'll show what the steady state actually is. So you have these two qubits. Of course, they're going to have some frequencies or some energy level spaces. Let's say they're not the same. They're not at the same frequency. The width of these peaks in frequency tells you how strongly they're coupled to the waveguide. And the requirement for this protocol is that you apply a drive on both of these qubits at a frequency in between the two qubit frequencies. Now, under those conditions, you get a steady state that looks like this. I won't go over the math. You can look at this paper over here. It's just 5 or 6 lines of very simple math that gets you to this steady state. And you'll notice that it's a superposition of the ground state and the Bell state. And the coefficient of the Bell state is given by this factor over here. So it's directly proportional to omega, which is how strongly you're driving the qubits. And it's inversely proportional to gamma, which is how strongly they're coupled to the waveguide. So if omega is much larger than gamma, I have almost a perfect Bell state, and it's a steady state. So as long as these two drives are on, my two qubits are going to remain entangled. So I don't have to keep on re-preparing the entanglement. It's just going to stay there for as long as I want. So that's something we're interested in implementing. One more important thing about this is that it's independent of the distance between these two qubits. Of course, there are some practical limits. The photon is going to travel from the first qubit to the second qubit. If they're very far away, the photon is going to decay somehow. But for all practical reasons, I don't really have to fine-tune the distance between those two qubits. They can be arbitrarily far away. That's why this protocol is really interesting. For a quantum network, you don't have to worry about how far away your two chips are. As long as you have this system, you can have entanglement between them. So let's dive into the problems that we face if we try to actually implement this. These red arrows are everything that can go wrong. You can lose your photon in the waveguide. Of course, it's not an ideal waveguide. And of course, you can lose your photon while it's inside the qubit. Your qubit isn't perfect. It has a certain relaxation time and a certain dephasing time. So these red arrows are all the bad things that can happen. This gamma over here is what we call the good loss. It's because it's the qubit losing the excitation to the waveguide, and that's necessary for the protocol that we want to implement. So we want the gamma to dominate over all of these bad loss rates, the one indicated with the red arrows. Now here's what happens if we have transmission loss. You lose your photon over here. These are simply some simulations that show how your entanglement goes down. I'm using concurrence as a measure of the entanglement. A concurrence of 0 means you have no entanglement. You have a completely separable quantum state. A concurrence of 1 means you have a perfect Bell state. So you can see that without loss, if you simply drive strong enough, you can have perfect entanglement. But as soon as you introduce any amount of loss, even let's say 5%, you can see that the entanglement really goes down a lot. So it's really sensitive to waveguide loss. The second kind of loss, of course, is the on-site decoherence, which is simply because the qubits aren't perfect qubits. You can see that this simulation over here is assuming that it's a perfect qubit. You can see that there's a large dark purple region, which shows that we have perfect entanglement. We can have perfect entanglement in this regime. As soon as I simulate with a 30 microsecond T1, which is a realistic number in the lab, you can see that this high entanglement region, the dark purple region, gets pushed up to stronger drive strengths, which means that in a realistic system, I need to drive more strongly to get the same amount of entanglement. So that's simply a glimpse of what goes wrong in a realistic system. Now, this is our version of the implementation. Now you can see this is the same picture I showed you a while ago. This cable was connecting these two modules over here. What if we simply replace those cables and we added a circulator? Now a circulator is important because remember we need a chiral waveguide. We only need photons to propagate from the first module to the second module. And this microwave circulator is an element that ensures that it doesn't let photons come backwards. So we had the hardware, we had the architecture, we simply had to make a small modification for this experiment. And this is a more cleaner diagram of what it looks like. You have these two modules. Each of them contains a chip with a transmon. The transmon is coupled to this waveguide over here. So the photon leaks into the waveguide, passes through the circulator, gets absorbed by the second one. And that's how we get this system that we're interested in. So this is just a quantum optical version, and this is what the actual experiment looks like. Now, of course, there's a few problems that we have to deal with. Is simply adding the circulator good enough? And the reason we ask this question is because the circulator is a very lossy element. We're going to have a lot of transmission loss with the circulator. So that's a question we're interested in answering. The second is, we need these two qubits to be equally strongly coupled to the waveguide. Remember the gammas in the previous plot, we need the gammas to be equal. Then of course, the third and most important question is, once you have entanglement, once you have steady state entanglement, can you actually measure your qubits and prove that you have entanglement? And I'll briefly discuss why that's an issue in this experiment. So we start off with simply measuring how strongly the qubits are coupled to the waveguide. And that's simply a measurement of the relaxation time of the qubit. You populate the qubit with a photon, you wait and see when the photon decays. That tells you how strongly you're coupled to the waveguide. So you can see that they're not really equal. In fact, they're off by a lot. One of them decays in 120 nanoseconds. The other one takes 270 nanoseconds. So that's the first thing that could go wrong. They're not equally coupled to the waveguide. Then we simply check what their frequencies are. And thankfully, they're quite close in frequency, where we can see we're driving Rabi oscillations as a function of the detuning. And you can see that these two qubits are around 25 megahertz apart in frequency. So for generating entanglement, we simply have to drive both of them at this central frequency, which I'm going to call epsilon 0. I'll skip over this slide because we're short on time, and I'll jump straight to the experiment. So how the experiment works is you simply drive the qubit for long enough so it reaches the steady state, and then you perform quantum state tomography on the qubit. Once you have state tomography, you have your 2-qubit density matrix, and you can calculate the concurrence and see how much entanglement you have. I'll skip over the technical details of the tomography part and jump over to the results. So this is the actual measured concurrence in this experiment. You can see that as we drive stronger and stronger, the concurrence goes up and then begins to go down. This is completely expected behavior. For qubits with finite coherence times, you can drive arbitrarily strong enough for a different physical reason that I won't dive into right now. But the important thing is you see steady state entanglement. You have a concurrence of around 0.1, which isn't great, but it's interesting because if you look at this plot over here, it's actually the steady state that's entangled. I'm measuring after a microsecond, 2 microseconds, 10 microseconds, and even 1,000 microseconds, and I'm measuring the same amount of concurrence, which means that my qubits can stay entangled for as long as I keep the drives on. This is simply the density matrix when it's in the entangled steady state. And the green is the measured one, and the black outline is what we predict from simulations. And it's in quite good agreement. We have 97% fidelity between the simulated and the measured density matrix, which means that we have a good understanding of the Hamiltonian for the system because we can accurately simulate the system. Of course, there's a problem with this because even though we have steady state entanglement, it's not the amount that we actually predict from the loss rates that we have in the system. Simply based on how bad the qubits are and how bad the waveguide is, we expect a concurrence of around 0.5, which we're not getting. And the reason was simply that these two couplings are not equal. The qubit couplings are mismatched, so you're not getting the highest concurrence that you can actually achieve in the system. And to fix that problem, we had to do some math that I won't go into, but this paper actually gives a glimpse of what's going on. Instead of driving both of these qubits at the same strength, omega, what you have to do in case of a mismatch is you also have to drive them with different strengths. So to counter the mismatch, you have to introduce another mismatch in the drive strengths, and that mismatch is given by this equation over here. So that simply means that the ratio of the omegas, the ratio of the gammas tells you what the ratios of the omegas should be. And if we plug in our numbers over here, the ratio turns out to be 0.66, which means if this is omega, this should be 0.66 times omega. And once we did that, we see that the concurrence actually goes up to 0.5. And that's the limit set by loss. So given this hard work, we were able to achieve the highest amount of steady state entanglement that's allowed, given the loss rates in our system. So this was interesting for a number of different reasons. First, you have two qubits on separate chips. Not only can you entangle them, but you can entangle them in the steady state. So let's say you have a quantum network and you need to perform an algorithm. You always have on-demand entanglement available. You don't have to prepare the entanglement. It's always available for you as a resource to use for your algorithm. And along with that, this was also the first demonstration of steady state entanglement between any two qubits that are far away. People have demonstrated similar things on the same chip, but it's the first time someone showed entanglement in the steady state between spatially separated qubits. So that's all I'm going to talk about right now. And just to summarize, we came up with an architecture that allows you to connect distant qubits together that live on separate chips. And then based on that architecture, we did a high fidelity 2-qubit gate, a swap gate between qubits. And along with that, we did a physically interesting experiment that doesn't really get you a huge amount of entanglement, but it's physically interesting because it's steady state entanglement. And that's all I have for now. And this is just an image of what the actual device looks like. For the entanglement stabilization, you have these two modules. They're connected by this circulator. And so just a blown up diagram of what the device looks like. You have this chip that's inserted into the module. This is how the cable enters the module. And this is the port you use for controlling the qubit and for reading out the qubit. That's all.
Excellent. Questions, please.
इससे पीछे जहाँ इसमें ये स्पेसिफिक डिस्टेंस आपने कुछ रखा है या लोग इसको कम भी कर सकते हैं?
ओ ये तो ये डिस्टेंस है, ये आर्बिट्रेरी है। तो इस प्रोटोकॉल का फायदा ये था कि हमें फर्क नहीं पड़ता कि क्यूबिट्स एक्चुअली कितने दूर है। तो ये जो केबल्स हैं ये मैंने कभी मेजर नहीं की, मैंने बस ये केबल्स एक आर्बिट्रेरी साइज की कट करके यूज कर ली। So this could work even for shorter cables or for longer ones, and that's the fun part of this protocol. It's independent of the distance, but there's of course some physical limit. If I make these cables way too large, let's say several meters, that's going to be problematic for a different reason, and that has to do with the Markovian approximation. So right now, if a photon leaves this qubit, it takes a very short amount of time to get to the second one. But if the cable is too long, there's going to be a finite time delay, and the Markovian approximation breaks down. You begin to see memory effects. So the protocol basically fails.
अच्छा एक चीज यहाँ पे जो प्लेन है जहाँ जो इक्विपमेंट्स का वो this is the surface ना, तो हम लोग उसको स्लाइस लाइक इस तरह स्टैक के तौर पे नहीं यूज कर सकते because it might reduce the which is कि जब वो easily transfer कर सकती है। स्ट्रक्चर चेंज कर दे तो हम लोग एक ही सर्किट पर ज्यादा क्यूबिट को इंस्टॉल कर सकते हैं, ऐसा हो सकता है?
डेफिनेटली। तो इसके अंदर जो चिप है इस पे आप देख सकती हैं कि अभी सिर्फ एक क्यूबिट और एक रेजोनेटर है। तो जो इंडस्ट्री है और जो बड़े लैब्स होते हैं वो बहुत बड़ी चिप्स बना सकते हैं, तो एक चिप के ऊपर भी सेवरल क्यूबिट्स आ जाएंगे। तो इस केस में हम एक लैब स्केल में, एक एकेडमिक लैब में हम सिर्फ प्रोटोटाइप कर सकते हैं इस तरह के आर्किटेक्चर्स। हम एक्चुअली इंडस्ट्रियल स्केल पे नहीं जा सकते फॉर अ बंच ऑफ डिफरेंट रीजंस। फैब्रिकेशन बहुत मुश्किल होती है और इंडस्ट्री में एक्चुअली फैब्रिकेशन इंजीनियर्स होते हैं जो ये काम कर सकते हैं। तो हमारे केस में हम बस सिंपलेस्ट पॉसिबल चीज में जाते हैं, लेकिन योर करेक्टर्स को स्केल अप करने के और बहुत एफिशिएंट तरीके हैं।
But I guess the whole point of this thing was to actually do it on different,
Exactly, on that different, spatially
separated.
Yes.
वो एक जगह पे आपने दो फोटॉन्स डीजेनरेट यूज किए थे, तो उसके वजह एक सफिशिएंट एनर्जी वाला क्यों नहीं?
गुड क्वेश्चन। तो उसका रीजन ये है कि जो ट्रांसमॉन है we treat it as a 4-wave mixer. So what that means is you need 4 photons for any process that you want to do. So what I mean by a 4-wave mixer over here is that one photon is going to be in the transmon. I add 2 more photons, and together these 3 lead to the 4th photon, which is going to be a photon in the resonator. That's how I transfer it from the transmon into the resonator. So for this conversion process, the Hamiltonian requires 2 additional photons, such that when you add their frequencies, you get the frequency of the resonator.
What's
So
this process called?
This is called a 4-wave mixing. You also see this in different materials in quantum optics for frequency conversion, things like that. You have a certain material. If you apply waves or photons of certain frequencies, they add up or subtract to give a photon of a different frequency.
Were you trying to ask, why can't, instead of having 2 photons of frequency omega, why can't you use 1 photon of frequency 2 omega?
Yep, because if we look at the Hamiltonian, it's going to have 4 ladder operators corresponding to 4 different photons. So let's say I want to generate the A dagger B term. That's what I'm interested in. I want to destroy a photon here and create a photon over here. So if I want this A dagger B term, I want to get rid of, so initially this Hamiltonian term had 4 ladder operators. It also had 2 more A's or A daggers. So in very simple words, you could say that you need to get rid of those 2 terms so that you're left with A dagger B. And that's the physical reason for why you need 2 photons to replace, so the amplitude of the 2 photon drives that you apply, they're going to replace 2 of the ladder operators, and what you're going to be left with is A dagger B. So if you only send 1 photon, you'll have a 3rd operator over here. So you're not really converting a photon from the transmon to the resonator. What you're saying is also possible, but you'll need a slightly different Hamiltonian for that. There are ways, that's called 3-wave mixing. If you don't have a transmon, there's certain other circuit elements that allow 3-wave mixing. In that case, you only need 1 photon to convert it from the qubit into the resonator.
More questions, please. All right, if not, then let's thank the speaker. And we have some tea and snacks for everybody.
Interesting work. Excellent.
Very interesting.